Hello everyone, welcome to the linear elasticity course. In this video, we're going to discuss the stresses and which is one of the essential measures of the elasticity or the continuum mechanics. We have discussed before the kinematical parameters and we defined the deformation, the strains, and the different component of the strains and how we can drive the strain from the deformation tensor or the relation of the strain to the deformation tensor, also the relation to the rotation tensor. These kinematical parameters, we have discussed them in two previous videos. In this video, we're going to discuss the stress. Stress, it means that we kind of have been moved to the kinetics, which is the second part or branch of the mechanics. We discussed the kinematics, which is just we were interested in the kinematical parameters that describe the deformation, and we define the deformation as change in the shape, change in the dimensions, or a change in the rotation or position of the continuum or a point within the continuum itself. Now we're going to move to the kinetics, which is the second branch, as I mentioned, for the dynamics or mechanics. I'm sorry. In general, it is kinematics and kinetics. Kinetics, it means that we are going to relate the motion, relate the deformation that this continuum is going to exhibit to the external forces acting on it. So I'm going to refresh your mind with something that we discussed before regarding the continuum mechanics when we were driving the equation, the equilibrium equation, starting from the mechanics of discrete system of particles. We said that a continuum generally, it is a composition of so many particles, and the count of this particle is tends to infinity, and each one of these particles is just a point. And even we define that the continuum is going to be consistent of or consists of so many particles that going to be located inside the core or the inside the continuum itself, like this case, while there are some other particles that will be distributed over the boundary, or in other words, over the surface. And we said that the type of interaction or forces that is going to generate over the particle that located in the core or inside the continuum will be different than the forces that is going to be acting or affecting on the particles, which are the red ones that already located over the surface. We said that these particles, they already in interaction with the surrounding particles except from the top. It means that there is kind of under coordination. It means that there are the number of the interactions between these surface atoms is different than the interactions between the core atoms, and this is one of the reasons that we do have some excess energy comes because of this difference in the interaction between the atoms on the surface and the atoms inside the core, and that's why we do have the concept of the surface tension, especially for fluids, for example. But it still exists in solids, but its contribution it is very negligible. But anyway, we said that this is the like a schematic of how the continuum is going to look like from inside and from the surface, that it consists of so many particles and each one of these particles is just a point. And as I mentioned, there are some particles that already located over the surface. And for some reason, this continuum is going to be subjected to some external forces. And we defined, if you remember, T, where T, this is like a surface traction, that kind of force acting on the particles acting on the surface or located over the surface of this continuum. In addition, there are definitely some other forces that internally acting or affecting on the particles that already located inside, and we define these forces as F vector, where F stands for the body forces, and we said that these body forces would be any type of force that affecting or acting on the particle that already located inside the continuum core. And we give examples, lots of examples of these body forces. These body forces would be interactions between the particles, it would be the weight of the particle, it would be some, it means that weight, it means gravitational force, it would be electrical field, or it would be electrical force or magnetic force, thermal force, any force that acting on the particle that located inside the core. This is known as, we're gonna collect all of these different types of forces into a body force. So this is the body force, right? And then we said, in the meanwhile, we said that any forces, the same forces that but affect on the particle that located over the surface, we're gonna give them a name as the surface tractions. Tractions, this is like a force. This is a common name that we agreed to give it to these forces that already acting on this particle located over the surface. But you should understand that this T, it is kind of a special type of the force that already again acting only on the particle that located on over the surface. And if you remember, when we tried to drive the equation, the equilibrium equation, from the discrete system of particle going to the continuum mechanics, we had to apply the divergence theorem, that we had to convert the integration of this surface interaction that is going to be located, because to collect all of these surface interaction, we have to do integration but over the surface. To convert the surface integral into volume integral so we can proceed and to drive the equilibrium equation that we basically use for the continuum mechanics, we had to convert the surface integral into an equivalent volume integral through the divergence theorem, if you remember, right? And to do so, we had defined T, which is the surface traction, in terms of another tensor, and we give this tensor a name as sigma, for example. And we said that this is commonly known, this tensor with this sigma is commonly known as the stress tensor. This is the stress tensor that I'm talking about. And this n, it should be the normal, the unit normal vector, or this is the normal vector, the unit normal vector to a surface. Like, as I said, this is like and this is vector. This is simply like force vector acting over a surface whose normal is n. So if we did multiplication of n, or dot product of n, which is the normal vector to this surface, to the sigma, which is the stress tensor, and this tensor is a second order tensor. If you remember, this is second order tensor. It means that this tensor, it should have like 9 independent components. But then after that, when we drive the equation, because of the equilibrium, the moment equilibrium, we found that the skew symmetric part of this tensor, if you remember, it was 0 or vanishing. It means that this tensor by default is symmetrical tensor, and this is the fundamental concept of the classical mechanics. Based on the classical mechanics, this tensor is a symmetrical tensor. It has no skew symmetric part. It means that this 9 component can be reduced only to 6, will be reduced only to 6 component as independent component. This, we defined already this relation, and this what defined to us or brought to us the stress. So the stress here, you could say that this T, this vector, it is kind of external force acting over a surface, which is the exterior surface or the boundary of the continuum. And through this relation, through this equation, we kind of driving the effect of the surface traction on the continuum. What's gonna happen to this continuum because of this surface traction? If this continuum is gonna be subjected to some forces, these forces or surface tractions will definitely do something to this continuum. This something is going to be in the form of deformation. It's going to do some changes in the shape, changes in the dimension, rotation to the continuum, as we discussed before. This, it means that this surface traction should provide or make some kinematically changes to this continuum. But in the meanwhile, it will produce some stresses. And that's why through this relation, we said that, and this is stress, this is the equivalent form of the surface traction, but how this surface traction is going to affect the continuum as overall, right? So you could consider that this stress is very similar to this T. This stress is a force, like kind of a force. Or you could consider that this traction, surface traction, this is like a stress. It means that this sigma and tau both are the same. Both are the same effect because of the external force acting on the continuum. But you could consider this is like a transformation, like these the forces that already located over the surface. And on the right hand side, this sigma represents how these forces is going to affect the continuum, right? So the first part here of today's video actually, or this lecture, is to introduce to you this surface tensor or the components of the stress and how they already related to the surface traction. And this is the first part of the today's lecture. So the first part here is just to understand the relation between the stress and the surface tractions. Again, the stress is sigma. This is stress, this is the sigma, which is a second order tensor. T, this is the surface traction, which is kind of a stress or kind of force. So people could think of the sigma as a force, like kind of a different form of the force, and T is a stress or a force. Sigma is a stress or a force. It means that we can simply convert the force, or we can drive the stress from the force or the force from the stress. So both are the same. It means that here we are incorporating the force things. So the relation between the stress and the surface tractions, which are the forces acting on the particles located over the surface. These surface tractions are only the forces acting on the particles related over the surfaces, over the surface of the continuum, and how these surface forces would affect the continuum in terms of stresses, right? So you could consider that this sigma, this is something internally, something that's related to the overall continuum, while this T, this is some external things that comes from external objects or things acting on the continuum itself. So the relation between the surface tractions and the stress in the vector notation is T, where T should be vector. You should understand that T, this is the surface traction vector. It is already a vector, and we could give it another name, as I'm going to show you right now. And this sigma is the stress tensor. This is the stress tensor. It is a second order tensor, definitely, and it is the unit normal vector that is normal to the surface itself, and it is a vector as well. So from the tensor calculus or the vector calculus, the multiplication of vector, the dot product of a vector times tensor, this gives a vector, because the dot product gets rid of the vector. So the tensor will have delta I, delta j, or delta k, delta j, and this will have like delta I or delta j. So the dot product gonna get rid of one of the vectors, so we're gonna end up, or the unit vector, we're gonna end up with only one unit vector. It means that this equation is equivalent. The left hand side is a vector. Here we have tensor dot product with a vector gives a vector. This is the relation between the stress and the surface tractions in the vector notation. In the index notation, these are the components. Like this is the I component of this of the surface traction, and this is the J component of the unit normal, and this is sigma Ji, which is the Ji component of the stress tensor. The stress tensor, since it is a tensor, it should have two indices as already given here. So this is the representation of this relation, but in the index notation. So for example, if I decided using this one, if I decided to write all the components of this vector, so Ti, it is a vector, so it should have only three components. So for example, in case that I, it is x, so I should end up with Nj sigma j but x. As you can see on the right hand side, j is a repeated index. It means that this is a dummy index. Dummy index, it means that it should be repeated, and then we're gonna sum. It means that we're just gonna have here nx sigma xx. This is one term, in this case sigma xx, plus ny sigma yx plus nz sigma zx. If you sum this, calculate this term and this term and this term, and you sum all of them together, we're gonna end up with the force that acting parallel to x. And we're gonna explain all of these different terms right now. But now let us write the y component. In case that I is already y, this is gonna give us nj sigma jy equals the nx, in case that j is equal x, so sigma xy plus the y sigma yy plus the nz sigma zy. Then the z component of the force vector or the surface traction vector, it is nj sigma jz equal the n x sigma xz plus the n y sigma yz plus the nz sigma zz. Make sense? So these are three components of this vector, and people who can give this one, because this vector is already dependent on the stress component, these different components of the stress. So people can give this one as the stress vector. We could name this one as a stress vector because it is already vector. But this component of the sigma xx, sigma xy, and so on, these are the component of the stress tensor. So you could consider this is like kind of transforming the stress tensor, which is already a second order tensor, into an equivalent first order tensor. Some people deal with it in this form, but originally you should understand that this tx, ty, tz, this should be the stresses or the forces acting on the particles located over the surface of the continuum, and this sigma xx, sigma xy, and so on, this sigma component already related, or this is the result of the surface traction that already acting on the continuum. As you can see generally here, we do have sigma xx, we do have sigma xy, yx, we do have sigma zx, then we do have sigma xy, we do have sigma yy, and we do have sigma zy, sigma xz, which is the opposite to this one, like the transpose of this one, and sigma yz, the transpose of this one, and sigma zz. So you could consider that this is like a diagonal. These are the diagonal component of the stress tensor, and these are the off-diagonal components. So as you can see, we do have 9 different components of the stresses that are related to the stress vector or the surface traction. So generally we can write these sigmas. It means that generally the stress tensor, it has 9 independent components generally, or 9 components as sigma xx, sigma yx or xy, and sigma xz. Then we do have here the sigma yx, sigma yy, and sigma yz, and then the sigma zx, sigma zy, sigma zz. But we had proved before, when we derived the equilibrium equation for the continuum, that this tensor, it is a symmetrical tensor. So what does it mean, symmetrical tensor? It means that it will have 3 components over the diagonal, and the off-diagonal components are equivalent. So some of the properties that we should understand or consider for this tensor, that it's sigma ij equal the sigma ja. Ji, it means that it is a symmetrical tensor. It means that sigma xy is typically the same like sigma yx, as we derived it before, that before we proved that the skew symmetric part of this tensor, it should be vanishing or it should be 0. It means that it should be symmetric. Make sense? So these are the different components, and this is how the surface traction is going to be related to the stress component that we're going to have here. But to understand this different stress component, even if you remember, when we discussed the strain tensor, we said that the strain tensor, the strain, it measures 2 things. Changes in the shape and the changes in the dimensions. But we do have the rotation as a rotation tensor to give like rigid body rotation of the object. This is the rotation tensor. Because we discussed, as we discussed in the previous video, that the deformation tensor, it is a general tensor that has 9 components, and we can split it into symmetric and skew symmetric bar. The symmetric is going to give us the strain tensor. As we discussed, this strain tensor has 6 independent components. The 3 components over the diagonal, we name them normal strains, and these normal strains give us changes in the dimensions along x and y and z. If you remember, just to refresh your mind about the strain things, we said that in case that we do have, let us consider that you do have this square or this cubic shape, and in case that we do have epsilon xx, it means that this is normal strain that is parallel along the x-axis, and this normal strain will result in some stretch or contraction in this box, right? It means the box is still box. The shape, there is no changes in the shape, except that there are some changes in the dimensions, like the length has been increased in this way, right? The same thing in case that we do have like epsilon yy. The epsilon yy is gonna do some changes in the dimensions along y, is gonna do some stretch along the y direction, and so on. So the epsilon yy, epsilon zz, and epsilon xx, these are normal strains, and we used to give them a name as normal strain, right? That these normal strains describe the change in dimensions only, in dimensions. Then also we discussed that the other three components, because the strain tensor has 6 components, the epsilon xx, epsilon yy, epsilon zz describe the change in dimensions as normal strains, but the other component describe the change in the shape, which is that's why they already commonly known by the shear strains. So even if you remember, this is an example of a shear strain, like if you do have this box here, and for some reason that we're gonna enforce this surface on the top to be moved in this direction, and this one is gonna be moved in the other direction. So here definitely we're gonna end up with a change in the shape. It was a square, now it became diamond shape. It means that we do have like epsilon. If this is the xy plane, this is the xy plane, so we're gonna end up with epsilon xy, which is definitely a shear strain. So the shear strain gives us change in shape, right? These are the different types of strains, nothing more. Normal strain to describe changes in dimensions along x, y, or z, or shear strain that describe changes in the shape or the changes of a plane, like epsilon xy, changes of the plane xy, epsilon xz, the change in the plane xz, and so on, like epsilon yz, the change of the plane over the plane yz. So these are the strain component, which they already just 6 components, 3 on the diagonal and 3 off diagonal component. We do have a similar situation here for the stresses. We do have 3 components, sigma xx, sigma yy, sigma zz, that they already located over the diagonal, and we do have some off diagonal components. If you remember from the mechanics of material class, we used to give a name to this diagonal component, the normal strains. So it means that they should somehow conjugate or relate it to the normal strains, or do similar effects like the normal strains. The same thing, this off diagonal component from the mechanics of material class, we used to give them a name as shear stresses. So they should be conjugate or somehow do the same effect like the shear strain to a box like this one or to the continuum, right? So let us investigate these things and how these stresses could be related to the surface tractions. So to explain this, let us consider that you do have this cubic shape. Like assume that you do have a continuum, and this continuum simply is just a cube in this way. Okay, and let us set up some coordinates, like this is like the x-axis and this is the y-axis, and we do have here the z-axis in the 3-dimension definitely. Then let us assume that we do have some force. So for this surface forces, we do have Tx. Tx, this is the surface traction that is going to affect on all the surfaces of this box. Not just one surface, it's going to affect this. Tx is going to, this is the same force that is going to act over the continuum in general, like over all the surfaces. So for example, we can, as you can see, we do have here 3 terms for each vector, for each component. Tx, it has 3 terms, 1 term, 2nd term, 3rd term. This term is nx. What is nx? This is nx. This is the surface whose normal is x-axis. In y, this is the surface that whose normal is y-axis. In z, this is the surface whose normal is z-axis. So what does it mean? For example, any surface in terms of mathematics, we can define the surface by its normal. Now, because there is no specific, for example, the vector, it can be defined by the end, the start, like a line. The line has 2 ends. So for example, like this line, I can define this line as line or sector AB. A point is just a point A. We can give it a name. But how we can name a plane? To define a plane, we need the normal. To call the plane, it is called by its normal. The normal to the plane itself. So for example, what is this surface? This plane. This surface is just a plane, right? Or just a surface. This surface, what is the normal to this surface? Is it X or Y or Z axis? It is X axis. So we're gonna give a name to this surface, like we already giving a name to this surface as an X surface. How about this surface? This surface whose normal, this surface, its normal is Y axis. So we're gonna give it a name as NY. This one is another surface whose normal is Z. So this is gonna be like NZ. So when we mention here NX, we mean by NX this surface. When we mention NY, we mean by the NY this surface. When we mention NZ, we mean by NZ this surface. Make sense? So these unit vectors refer, each one refers to a specific surface. Like NX refers to the surface whose normal is X-axis. NY refers to the surface whose normal is Y-axis. NZ refers to the surface whose normal is Z-axis. Very simple. Make sense? Then what? If we consider this force Tx, Tx is going to affect on the three surfaces, not just one. Tx, the same force vector or the same force component that is going to affect this on the surface whose normal is X, is going to affect on the surface whose normal is Y, is going to affect on the surface whose normal is Z. So let us consider just Nx component, the first component here. So for example, to have a Tx acting on the surface whose normal, Tx, it means that the force all the time it should be parallel to X. So we're gonna have over this surface Tx, or let's say, I'm just gonna assume it in this direction, like we do have here, Tx, and over this surface we're gonna have another Tx, which it should be the same force, and over this surface we're gonna have Tx. Remember that Tx, it means that the force component, it should be parallel to the X-axis because this is the X component of the T vector. This T is a vector. It has three components. This is the X component, so it should be directed all the time to the X direction, right? No matter what the surface is that this force is acting on. If this force is acting over the surface whose normal is in X, it's gonna do something to this continuum. If this Tx is acting on the surface whose normal is Ny, is gonna do something in the continuum. The same thing Tx, if it is acting, the same force, if it is acting on the surface whose normal is Nz, is gonna do something else to this continuum. So to make it simple to understand these things, let us work in two dimensions. Assume that let us just pick the XY plane. So if we choose the XY plane, we're gonna have here the square. This is just the XY plane, where this is the X-axis and this is the Y-axis. Remember that this plane, it is surrounded by four surfaces. This is one surface whose normal is X, and this is another surface whose normal also is X, and there is another surface on the top here and the bottom. These surfaces, their normals are the Y-axis, right? Like this is NX and NY. Make sense? Now let us define the Tx. Let us just consider this Tx that acting on the NX surface. So we have Tx here. If this Tx is acting in one direction, this continuum is going to move, right? If there is nothing on the other side, what's going to happen? Assume that this is like a surface, right? And this is like a box, and you're going to put this box with some force Tx. So this box is going to move. And this is basically is going to give us rigid body movement, and we don't need it. This is what we used to define or assume in the dynamic class. But here in the continuum mechanics, we need to show some deformation in the continuum. To have deformation in this box, it means that it should be pulled from both sides with two opposite forces with the same magnitude Tx. Because if one side is with a force bigger than the other one, for example, if this force is bigger than this one, is going to move to the right. If this force is bigger, it's going to move to the left. Forget about, we would like to prevent any kind of movement. So in this case, this Tx and Tx, they should be equivalent. They should be equal, right? So if you have something pulls in the right and something pulls in the opposite direction, what should be happening to this box? It's going to be stretched, right? So this is going to result in some stretch in the continuum, right? This continuum, it will be stretched. which is gonna be very similar like this case. It means that this continuum will produce some epsilon xx that we used to give it a name as normal strain, right? But remember that this Tx is already acting on the surface whose normal is x. This Tx acting on the surface whose normal is x. So Tx acting on the surface whose normal is x is going to produce sigma xx. It's going to produce a normal stress or a stress known as sigma xx. Make sense? So it means that this type of stress that is going to be produced, so this Tx is going to do two things. It will first of all produce epsilon xx, which is normal strain, because definitely we end up with some changes in the dimensions along x direction, right? In addition, it will produce some epsilon yy, because why there is epsilon yy? Because as you can see, we do have an increase, we do have some increase in the lengths. Definitely the width in the y direction is going to change. So it means that we do have changes in the x direction or the dimensions of the continuum. There is no change in the shape, still box, but it is elongated and contracted from the y direction. So in the x direction, the length has been increased. So there is a change in the dimensions along x-axis, and there is another change in the dimension along y-axis. So that's why we do have two normal components of the normal strain. We do have also normal strain, but along the y-axis. But generally, you could consider we end up with some changes. It means that we're gonna end up with some normal strains along x and y. But in the meanwhile, we're gonna end up with sigma xx, which we're gonna give it a name normal stress, because it do the same effect like the normal strains. It looks like we're already subjecting this continuum into some stresses. These stresses, it will result, this is the reason behind this new shape, will result in some stretch in the continuum along the x direction. And this is conjugate to this function or this equation here, that Tx, when it affects on the surface whose normal is x, it's going to produce sigma xx. Make sense? But how about this term? In case that Tx acting on the surface whose normal is ny, it should provide sigma yx. It should produce sigma yx. So let us investigate the type of this sigma yx. We proved here that sigma xx is a normal stress. Why? Because we're gonna end up with the changes in the shape, in the dimension. There is no change in the shape except the dimension. So that's why we're gonna give it a name as normal stress, as we did with the normal strains. Make sense? Now let us consider the other situation, the same two-dimensional box here. In this case, and again, this is the x-axis, but this is the y-axis. And now we gonna use the same Tx, but Tx here, this force was acting on the surface whose normal is x-axis. Now I'm gonna make this force acting on the surface whose normal is y-axis, which is this surface. This is the surface whose normal is y-axis. This is the ny surface. Make sense? But it's still the same force, which is Tx. Again, if you subject this continuum into one force from one side, it's going to roll, or give some kind, it's gonna start to tip over and roll over the surface. And this is like kind of rigid body motion. But we don't need any rigid body motion. We need deformation. So it means that we have to subject the other surface, the bottom surface, with the same force to end up with some deformation in the continuum. So we're gonna have, but if this T is bigger than this one, is gonna roll in this direction. If this T is bigger than this one, is gonna roll up in this direction. We don't need to have any rollment or rolling of this continuum or rigid body motion except deformation. So it means that these two forces, they should be equal and opposite, very similar like what we did for Tx over these two surfaces whose normal, their normal was the x-axis. We're gonna repeat the same but over the surfaces with ny. So what does it mean Tx over this surface? It means that, assume that you're already holding this surface and you're just gonna push it in this direction. So this surface will leave its location. It will be, this surface is going to rigidly move in this way. And we're gonna do the same, but for the other surface, it's gonna move in the opposite direction, like you're already pushing the other surface to move rigidly, without rotation, without anything, just move, slide over the same line. So this is gonna end up with a new shape. If we try to do so, we're gonna kind of shearing or squeezing this box. So we're gonna end up with a chain. This is the new shape. We're gonna end up with a change in shape, but there was a change in dimensions. So what does it mean? It means that here we're gonna end up with a shear strain. We're gonna end up with shear strain, which is epsilon xy, or a change of the plane xy plane, which is the xy plane. So, and this is very clear that we end up, because this is very similar to the shear strain case. So definitely, in case that you have the same force, which is Tx, but acting on the surface whose normal is y, this force will produce shear strain, and definitely will produce a stress, which is this stress. According to this equation, the force Tx acting on the surface whose normal is y is going to produce a stress. This stress is called sigma yx. So what does it mean yx, or what is the type of sigma yx? So the other thing that this force will produce is sigma yx. Since this sigma yx, it should be conjugate to the shear strain, and since we define this deformation or a change in the shape as shear strain, it makes sense to give a name to this type of stress as shear stress. So we could say that the shear stress and the shear strain both describe changes in the shape of planes, but the normal stress and normal strain both describe changes in the dimensions of the object. Because of what? Because of the external forces acting on different surfaces of the continuum. If we try, this is in two dimensions, so we'd have only x and y plane or dimension. If we try to work over the three dimension, the z-axis, so we're gonna end up with the other third component. So we have here sigma zx definitely is gonna be shear strain, but shear stress over the zx or xz plane. Make sense? If we repeated the other things with the other component ty and tz, we're gonna end up with the same conclusion. So generally we could say that any component that with the same two indices like x, x, y, y, and z, z, these component, this commonly known as, we agreed, this commonly known as the normal stresses. And these normal stresses, they describe changes in dimensions along x and y and z, and they conjugate or related to the normal strains along the x direction, y direction, and z direction. Make sense? But how about the other components here? The off-diagonal components. The off-diagonal components, they describe this commonly known as the shear stresses. Why shear stresses? Because they are conjugate to the shear strains, and they describe the change in the shape of their planes. Like sigma xy describe the change in the xy plane, sigma xz describe the change in xz plane, sigma yz describe the change in the YZ plane. Make sense? So from this part here, we studied the relation of the stress in relation to the surface traction, and we said that this surface traction could be called as a stress vector or the surface traction, and these are the equation. These are the different components of the stress vector in terms of the stress tensor, right? And we defined that when we investigated these forces and how they would affect the continuum, we end up that we were able now to understand what does it mean normal stress, what does it mean shear stress. These terms that had been defined to you before in the mechanics of material, and probably you have no clue what does it mean normal stress or what does it mean shear stress at that time. You just used to use these keywords, but there is no physical meaning at that time was given to you to explain what does it mean normal stress or shear stress in the mechanics of material class. Now in this course, it is important to understand what does it mean normal stress and why it is related to the normal strain. The same thing for the shear stress and the shear strain, and how they already connected or related to the surface tractions or the stress, the component of the stress vector that already acting on the continuum, or in other words, these are the surface traction that acting on the particles located over the surface of the continuum. Make sense? And this is the first part of the today's video, is just to understand this relation. Make sense? Another thing also related to this part before we finish it is, if we consider, since this is a vector, right? Since this is a vector, and this vector has three components as tx, ty, and tz. These are like forces along x, y, and z directions that acting over the different surfaces of the continuum. Generally, any vector, since we already have these surfaces like flat surfaces or straight surfaces, but generally if we said that we'd have a surface, whatever this surface is, like let us use different color here. So we would have generally any surface, and this surface, it will be subjected into some external force, T vector. This T vector will have three components, one along X, one along Y, and along Z. It means that we can decompose this one, assuming that these are the directions of, like this is X axis, this is Y axis, and this is Z axis. So we can decompose this one into three components, one along X as Tx, one along Y as Ty, and third component along Z as Tz. Right? These are the three components of this force vector. But there is another option, that probably that this surface whose normal, let us assume that this surface has a normal as n. So as you can see, this is the direction of n, which is the normal to this surface. It means that this surface, it is not oriented to the x-axis or the y-axis or the z-axis, or in other words, that the normal of this surface, it is not considered or parallel to neither x nor y nor z. It means that it is not parallel to any one of these. It is located in another plane. And for some application, we might be interested to decomposing this force vector into two components. One component that is already normal to the surface, and another component that is perpendicular to that normal or tangent to the surface. You got my point? Like in some cases, we probably would require, or we are required to decompose this T into two components. One component is normal to the surface, completely perpendicular to the surface, and other two components that would be parallel or tangent or coincident to the surface. So these are like T tangent component. Like you do have like the acceleration in the dynamic class, for example. We had the normal acceleration, we do have the tangential component of the acceleration. It is similar to this situation, like you have a force, and for some reason we would like to decompose this force into two components. One is normal, one is tangential to the surface or tangent to the surface. So generally this force tensor, or this T tensor here, that had been defined in the vector notation in terms of the stress, we can, this tensor, or this vector, this is not a tensor, this vector can be decomposed into two components, one is normal, one is tangential. So simply we can write that T vector in the vector notation equals T dot n times n, where n is the normal vector to the surface, and T, this is the vector itself, this is the T vector, which like this one, plus the n, which is the normal vector, cross product of the n, which is the normal vector, cross product of T, which is the force vector or the stress vector. Make sense? So now this is like you're already decomposing the stress tensor into symmetric and skew symmetric parts, but this is, since this is a vector, so we're gonna decompose this one into normal component and tangential component. So this definitely is gonna give us the normal part or the normal vector of the force vector, and this is the tangential. All of this, it should be the tangential vector. This is the tangential vector, and both these still the tangential vector. And both are still vectors. Why vector? Because simply the dot product of two vectors gives scalar quantity, but in itself it is still a vector. So this term is a vector that represents the normal vector, and the cross product of two vectors gives vector, and the cross product of the vector with the other vector, which is n, gives also a vector. So this is still the tangential component of the of the vector itself. Make sense? So from this relation, we can end up or conclude that generally the Tn will instance for the normal component. This is the normal component or the normal force or stress tensor. This is the normal part or the normal component of the stress vector. I'm sorry, it should be the stress vector, right? This normal, it should be scalar. It is a scalar quantity. Scalar. Here I'm talking about the component itself. I'm not talking about the vector. I'm excluding the n. I'm just work over t dot n. So this equals the t vector dot n. So this definitely is going to give us a scalar quantity, which it could be written as the ti in the index notation. So this is in the vector notation, but this is in the index notation. So simply, or it can be explicitly written, because I in this case is going to be a dominant index. So we can write this one as tx nx plus the ty ny plus the tz nz. Make sense? So this is going to give us the n component of this tensor or this stress vector, I'm sorry. And the tangential component, the tt, where t stands for tangential component of this one, the tangential component, it should be, this is a vector. So I'm going to pick the components only of this vector. So the tangential component also is going to be a scalar quantity, or the tangential value of this force. Like you already have a force and you're going to decompose this force into two components. One component is normal and the other component is tangential. So the magnitude of this tangential component is going to be the square root of the magnitude of the t vector square negative the tn square. What is the magnitude? This is the tangential component. This is the tangential force or stress vector or part of the stress vector. Make sense? How much is the magnitude of a vector? The magnitude of a vector simply is going to be the square root, as you had in the mathematics, the square root of the x component square plus the y component square plus the z component square, because in case that we're already working in 3 dimension, this vector, it has 3 components. One is along x, one is along y, one is along z. You're going to square all of these and sum under the square root. This is going to give us the magnitude. If you square the magnitude, it means that we're going to end up with tx squared plus ty squared plus tz squared negative tn squared. So if I decided to write this one in terms of the components of the stress vector, so we're going to have the tangential component is going to be the square root of this magnitude square is going to, the square is going to get rid of the square root. So this is going to give us the tx squared plus the ty squared plus the tz square negative the t normal square, and we define the t normal as the sum of all of these different terms, which is going to be the negative of tx nx plus the ty ny plus the tz nz. Make sense? All of this under the square root, this is going to give us the tangential component of the force of the stress vector or the surface traction. Make sense? So this is the relation of the stress or the stress in relation to the surface tractions. What I'm going to do right now, I'm just going to give you a very quick example on these equations or relations that we discussed here. Then we're going to move to the second part of this video. Let us consider this example on these equations or things that we discussed so far with reference to a rectangular Cartesian coordinate system, which is x1, x2, x3. This is like x, y, and z. So we can even replace this one like x and y and z, as we used to define the Cartesian coordinate as x, y, and z. But you can give it some textbook, or some people would give it like x1, x2, x3 to refer to the x, y, and z. It is still the same. the components of the stress direct. Direct, we said that this is a second order tensor, right? So the stress component or the stress tensor is already given with these different components. We do have 200, 400, and so on. Your objective is just to observe the location. This should be sigma xx, sigma xy, this is sigma xz, this is sigma yz, and so on. So anyway, we already given this stress tensor, and the unit of this stress is PSI. PSI, this is equivalent to pound divided by inch square, which is gonna be the pressure unit in the American system. And if you remember from the mechanics of material class, that the PSI is or the megapascal or the pascal, these are the units, or the unit of the stress is the same unit as the pressure. It is force over area, so it is pound over inch square. It means that this is force over area. This is the unit of this stress tensor. So the stress tensor is already given, and it is required to find the stress vector. What is the stress vector? It is T. According to this expression that we define, T equals as a vector equal the n dot sigma, which is the stress tensor itself in the vector notation, right? This is the equation that we supposed to use, and it's normal. It is required to find the stress tensor and its normal and tangential components at the point on a plane, at a specific point on the plane, where this plane it is defined by this scalar quantity. It is constant. It means that it should be scalar quantity with x1, which like x, we can write this one like x. I can write this phi as a function of x, y, and z equal the x plus 2y plus 3z. It is a scalar field. This is a scalar. That's why he mentioned that it is constant. It is a scalar field. All right. With this equation, so just a constant value or just an equation depending on the xy coordinate that should be substituted at any point, it is required to calculate if this is the plane or this is the surface and this is the stress. Beyond this surface, what should be the surface, the stress vector acting over this surface? Assume that this surface belongs to a continuum, and this surface was defined as a scalar field with this function phi, and we are interested in finding the stress vector that it should be acting over this stress or over this surface at a specific point to give us this, to produce this stress. We said that the stress tensor, it is produced because of some surface tractions acting on the particles located over the surface of the continuum. So assume that this is the surface, and we are interested in finding these external forces, these external tractions, this stress vector in terms of to give us this stress tensor. Okay. So what should be T then? This is the equation that we supposed to use. So we defined before up that Ti equal the Nj sigma j I in the index notation. These are the different components as we define them up there for the stress vector in terms of the stress components, right? This like Tx, Ty, Tz, Ni, Nj, sigma ji. So I'm gonna start from this index notation, then I'm gonna drive these different components. Also, but to do so, we need to define the different components of the normal vector. It is a vector. So it has x component, it has y component, and it has z component. So to drive the normal vector from mathematics, the normal vector to a surface described as a scalar field, this normal vector, so here we need to drive the normal vector first, equal the gradient of this scalar field divided by the magnitude of its gradient. This is from mathematics class. Make sense? So simply this normal vector, it will have three components. We are seeking these three components, but we have to find the gradient of this scalar field. From the gradient of a scalar field, as we defined it before, the gradient of a scalar field, it should be the partial derivative of phi with respect to, or the field itself with respect to the xi. If we decided to get rid of this is the vector notation. Now we're gonna use the index notation in terms of the components, delta I, where this should be, this is the unit vector indicate that these are the components. We can write this one into different components. So we're gonna have here like the partial derivative of phi with respect to x delta x, this is the x component, plus the partial derivative of phi but with respect to y delta y, plus the partial derivative of phi but with respect to z delta z. Make sense? So this is the in terms of the component, and these are the different components or the sum of these different components of this gradient. So your objective is just to find the partial derivative of phi but with respect to x, with respect to y and z from this given scalar equation. So phi is given as x plus 2y plus 3z. So if I ask you to find the derivative of this one with respect to x, this term will be 0, this term will be 0, we're just going to end up with just 1. So the partial derivative of phi with respect to x gives 1. So it means that this term will become delta x, 1 delta x. But how about this term? The partial derivative of phi but with respect to y gives, there is no y here, so this term will be 0, there is no y here, this term will be 0, there is y here, this term is going to give us just 2. The derivative of 2y gives 2 delta y. How about this term, the partial derivative of the same equation or the same function with respect to z, this term will be 0, 0, but this term is going to give us 3. So this, let me double check, no, this should be 2, not 3. This should be 2, 2x3, so this should be 2. Okay, let me just correct this one to have the same given, so you aren't going to be confused. So it was like a typo here, it means that this should be 2. Make sense? So the partial derivative with respect to z is going to give us only 2 into this term. So this term will be also 2 delta z. So we're going to end up with this nabla or the gradient of phi is going to give us at the end delta x, which is just 1 plus 2 delta y plus 2 delta z. Make sense? Then our objective is just to find the magnitude of this vector. This is the x component, this is the y component, this is the z component of this vector. So to find the magnitude of any vector, because this is simply a vector, right? To find the magnitude of any vector, the magnitude of nabla phi gives the square root of the x component, which is 1 square, plus the y component, which is 2 square, plus the z component, which is also 2 square. So this is going to give us 4 plus 4, 8 plus 1, this is going to give us 9. So this is going to give us the square root of 9, which will be 3. So the magnitude here of this gradient is going to be 3. So this is the gradient and this is its magnitude. So if you plug these things that we drive it here into this formula, we're going to end up with the normal vector. So the normal vector is going to be nabla phi divided by its magnitude, or the gradient of the field that describes the plane divided by its magnitude equals. This term we got it as 1 or delta x plus 2 delta y plus 2 delta z divided by this magnitude that we already got it divided by 3. So we can simply write this one as 1/3 delta x plus 2/3 delta y plus 2/3 delta z. Make sense? So this is going to give us the normal vector, and we can conclude that nx, the x component of this normal vector, is going to be definitely 1/3. And the y component of this vector is going to be 2/3, and the z component of this normal vector is going to be also 2/3. Make sense? Then also, so we already got the normal component, because to calculate Ti, we should have the components of the stress tensor, which is already given to us. All the components, we already have them here. But this thing that was missing is only the normal component, the nx and ny and nz, and this is what would drive it here. Then your objective is just to plug into this expression, into this equation. So simply, if I ask you what is the x component of this vector, the x component, it's going to be, as we wrote this one up there, Tx is going to be the Nj, is going to be the Nj sigma Jx, which definitely then you're going to repeat over the gamma index, which is J. This is going to give us the J, the nj is gonna be, J is gonna be x sigma xx plus the n, J is gonna be y sigma yx plus the n z sigma zx. Make sense? This is the first component. So simply, your objective is just to substitute for nx, sigma xx, sigma yx, and sigma zx as we already got them up there. So nx, we got it by 1/3. This is the nx component times the sigma xx. If you're gonna go up here to this tensor, sigma xx is already 200, sigma yx is 300, sigma zx we needed at 300. 400, 200, 400, and 300. So this sigma xx is already 200 plus the ny, we got it by 2/3 times the sigma yx that already up there as 400 plus the 2/3, which is nz, as sigma times 300, which is sigma zx. Then you're gonna do the calculation, you're gonna end up with a specific value for this component as tx. Then how about ty? Ty, you're gonna do the same. It's gonna be nj sigma j but y equal the nx sigma xy plus the ny sigma yy plus the nz sigma z but y. Make sense? Then you're just gonna plug these data. Nx, we got it by 1/3 times sigma xy. If we're gonna go up, sigma xy is already given by 400. It is not necessary that this tensor, it should be symmetric. Generally, the stress tensor, it would be symmetric or skew symmetric as we mentioned, but in the classical mechanics, it's gonna be symmetric all the time. But if we are talking mathematically, pure mathematics, it is not necessary that you do have this tensor symmetric. So it means that this component would be different than this component for some reason. But anyway, it is already given here. So sigma xy and sigma yz is 0 because we're gonna need, and sigma yy is already 0. So we're gonna end up here 1/3 times 400 and plus the ny, which is 2/3, but times sigma yy, which is already 0 up there, and the 2/3, which is nz times sigma zy is already given also by 0 up there. So we're gonna end up with something in terms as a number, as a value. The same thing if we did the calculation for the third component, so nj sigma jz. So the j is gonna be xz plus the ny sigma yz plus the nz sigma zz. Then you're just gonna substitute 1/3 times sigma xz. It is already up there by how much? 300, I think. Yes, 300. And we're gonna need the sigma zy, which is 0, and sigma z0, which is negative 100. So we do have here 300 plus the sigma ny, which is 2/3, but this one is already 0, plus the 2 over 3 times the negative 100, which is sigma zz. If we did the calculation, we're gonna end up with a specific value. So these are the three components of the vector. We can then arrange them in a vector form. Like this case, we can write here like t vector. It can be written, if we did the calculation, let me very quick do some calculations here. This is gonna be 2 over 3 times 100 plus the 2 or 800 divided by 3 plus the 200 divided by 3. This is gonna give us the 500. This value is 533.34. PSI, it should be the unit. So this clearly indicates that Tx, it is a stress. It is type of a force divided by an area. So this is a stress. If you multiply this Tx times surface area, this is gonna give us force. So that's why we can put this one as surface traction or the surface stresses or the stress vector. So that's why it is commonly known as the stress vector, because really it is a vector, but it is really a stress, but in the vector form. How about this value is gonna be 400 divided by 3. This is gonna give us 133.34. Again, the unit is gonna be PSI. How about this value is gonna be 100 negative the 200 divided by 3. This is gonna give us 33.34. 33.34 psi. Then our objective is just to write these terms, these components in the vector form. So the first component is 533.34 in the x direction as delta x, plus the second component is 133.34 in the y direction, and plus 33.34 in the delta z direction. This is the vector. This is the first part. This is the first requirement. It was required to drive the stress vector, and this is what we did for this vector. Then what should be the normal component and the tangential component? We have defined the normal component here as the TI/NI, which it should be the TX times NX plus TY NY plus TZ NZ. TX, TY, TZ, we got them. NX, NY, NZ, we already got them as 1/3, 2/3, and 2/3. So we just gonna plug or substitute directly into this expression here. For the Tn component is gonna be the TI/NI, which it should be the TX times NX plus the TY times the NY plus the TZ times the NZ. If we did the calculation, TX, we already got it by the 533, or you can just, we do have, this is the TX, this is the TY and TZ, and we already have 533.34 times 1/3, which is NX, plus the TY, which is 133.34 times 1/3, 2/2/3, plus the 33.34 divided by, or times 2/3, right? Because it is times 2/3. This is gonna give us the third term. If we did the calculation, we're gonna end up with a value. So that's why it is a scalar value for the Tn. This value is gonna be the over 3 times 2 plus the and we have here 133.34 times 2/3 plus the 533.34/3 plus this value. So we're gonna end up with 288.89 psi. Again, it is a stress. This is the normal stress, or this is, you could consider that this is the normal stress, or the stress component that is completely perpendicular to the surface, right? How about the tangential stress, or the tangential component? The tangential component is gonna be the square root of the magnitude of t square, the t vector, it's square, negative the normal component square, that we already got. So we need to calculate the magnitude. The magnitude of the t vector, it should equal to the square root of the tx square plus the ty square plus the tz square, that as we already got them up there, right? So we got tx, ty, tz, you just gonna plug them here and to calculate the square. So this is gonna give us the 533.34 squared plus the 133.34 squared plus the 333.34 squared. If we did the calculations, we're gonna end up with the magnitude. So this is gonna give us squared plus the 133.34 squared plus the 33.34 squared under the square root. This is gonna give us the 550 and 50.76 psi. Okay, so this is the magnitude. Then you just gonna subtract the normal component, the square of this one, negative the square of the normal component to end up with the tangential component. So the tangential stress that is parallel to the surface, it should be the square root of 550.76 squared, negative the normal component, which is the 288.89 squared. If we did the calculations, we're gonna end up with the tangential component in terms of the psi with this value. So this is gonna give us square negative the 288.89 squared under the square root. This is gonna give us 468.92 psi. So this is the tangential component, and this is the normal component of the stresses, or the stress vector acting on the surface, and these are the different components. So simply, this is like you already have the surface, and we already end up with one component of the stress that already perpendicular to the surface, and there is another component that is already tangential to the surface. This is the T normal and T tangential. With this value is already 468.90 psi as a stress acting over the surface, and the normal component we already got it by 288.89 psi as a stress. Make sense? So this is for the first part of today's lecture, is just to explain to you the relation between the stress tensor and the stress vector, or the stress tensor and the component of the stress surface fractions acting on the continuum. So now in the second part of this video, we're going to discuss the stress in relation to the body forces. What we discussed so far, we discussed the stress in relation to the surface traction, or in the other words, how the forces acting on the surface particles would affect the continuum. We said that these surface tractions, these T, will produce some stresses within this continuum, and we define these stresses as normal stress and shear stresses, right? And they have been related to the N, to the T, which is the surface traction, through T equals N dot sigma, as we explained up there, right? So this is what we discussed, the stress in relation to the surface traction. Now, in addition to the surface tractions, there are some other forces that would affect directly on the particles inside the continuum core. We said that there are some forces acting over the particles over the surface, and there are some other forces that are already acting over the particles located inside the continuum core. And these forces that acting on the interior particles of the continuum, they commonly known as the body forces, right? And we said that these body forces before, they are a lot. Any type of force, whatever it is, that acting on the particles internally, this is known as the body force. This body force, it would be due to the weight of the continuum, with the gravitational force, it would be electromagnetic force, or it would be magnetic force, it would be electrical force, thermal force, some even the interactions between the particles themselves. This is also kind of body forces, or even we may have some external forces that already directly acting on the particles of the continuum. So we would have the body force in the form of external force. So now we are interested in finding the relation, or studying the relation between the stress and the body force. Or in other words, as we said that these surface tractions, we proved that this surface will produce some stresses in the continuum. How about the body forces? Are these body forces going to drive or produce some stresses in the continuum? Yes. So there is a specific relation between the stress and the body forces, and this is what we are going to discuss. We have discussed this one, and we have proved this one through the equilibrium, or the equation of motion. When we derived the equation of motion starting from the mechanics of particles till the continuum mechanics, we end up with these equilibrium equations. If you remember that the equilibrium equation was in the vector notation, it was nabla dot sigma, which is the divergence of the sigma, which is the stress tensor, plus the body vector equals rho times u double dot, where u v sigma, this is a stress tensor, but this is the equilibrium equation. This is the equation of motion. If you remember, this is the equation of motion of the continuum, but in terms of the vector notation. This is what we derive before starting from the mechanics of particle, right? In the index notation, we can write this one as sigma ji comma j, where comma stands for like the partial derivative, or we can simply write this one in terms of the index as the partial sigma ji by partial x j plus the fi, which is the components of the force vector, equal the rho ui double dot u double dot. This is the acceleration vector. It is I, it means that it is a vector quantity. So this is in the index notation, and we simply said that we can get rid of the partial derivative to simply write this one as sigma ji comma j, as we did many times before, plus fi equals rho ui double dot. This is gonna give us the equation of motion, but in terms of the index notation, right? This is in the index notation. This is the equation of motion of the continuum. Make sense? If you remember that we said that this is all the time, this is direct, this is second order tensor, so this is tensor. But this multiplication is gonna give us vector, like nabla dot sigma, the divergence of a tensor gives a vector. And this force is the body force vector. This is the body force vector. And this rho times u, this is the inertia force. This term, all of it, it is the inertia force term. This is the inertia force term. Let me just remove this. This is the inertia force, all right, vector. It should be vector. Why? Because this u double dot, this is the acceleration. This is the acceleration vector. Make sense? So all of these different terms into this equation of motion are vectors, even including nabla dot sigma. But sigma itself is a tensor, but since it will be multiplied as a dot product, the divergence of stress tensor, second order tensor, gives a vector, and this is what we demonstrated or proved in the tensor calculus part of this class. So this is the equation of motion in terms of the vector notation and the equation of motion in terms of the index notation. This equation, the equation of motion relates the stress to the body forces. Or in other words, if we have been asked how the stresses are related to the body forces acting on the continuum, simply the stresses are related to the body forces through the equilibrium equation or the equations of motion. Make sense? As you can see, sometimes I say equilibrium equation, then I change to say that equation of motion. Is there any difference between equilibrium equation and equation of motion? Actually, there is no difference. We're still talking about the same equation, but people agreed that in case that we do have dynamics, or in other words, in case that the stresses acting or will be generated in the continuum depend on the inertia forces of the continuum or its particles, so this is the equation of motion. It means that if there is acceleration component, if there is inertia force, or there is something that related to the dynamics part, we agreed to give it a name as equation of motion, and this is what we basically you used to do in the dynamic class. In the dynamic class, your objective is just to form an equation of motion. Whatever for the vibration class or the dynamic class, form an equation of motion that describe the movement or the dynamics of the object, right? So this is the equation of motion since we do have this inertia term. In some other cases, how about if we are working in the static conditions? Static conditions, or let us work here in the elastostatic condition. Elastostatic, it is like static as you studied, for example, the static class or the dynamic. There was like some cases, some type of problem that have been covered assuming that is static. Static, it means that the velocity of the object is constant or the object is physically stationary, not moving. Or in other words, the static, it means that the dynamics or the movement or the state of the object does not depend on its inertia, or there is no change in the velocity of the object. Or in other words, simply we could say that in a static condition there is no acceleration. So the acceleration term, which it should be u double dot, it should be zero. Elastostatic, since we're already working in linear elasticity or in elastic bodies, it means that it will be deformable. There would be some deformation field that is going to be decomposed into rotation in addition into deformation field. So the static for any object that already elastic is commonly known as elastostatic equilibrium of the continuum. So the elastostatic condition, that this happens under the condition that there is no acceleration, and this happens in under two situations or two cases: that you have the object is already stationary, not moving, it means v is already zero, and which is the velocity is already zero. Or the other option, that this object is already moving but with a constant acceleration, we still have also the situation of elastostatic equilibrium. It is commonly known that in case that we do have static equilibrium, to give this equation the name as equilibrium equation, not equation of motion. Because equation of motion, it means that there should be a type of motion where there is one of the situation that the object is already moving under constant velocity. We're still having the same equation with this right hand side term is already zero, the acceleration will be zero, right? But people agreed, or it is commonly known, that we give a name to the equilibrium equation, to give a name to this equation as equilibrium equation or elastostatic equilibrium equation in case that there is no acceleration term on the right hand side. But this doesn't mean that the object is not moving. No, there is a special case that you'd have objects that move but under constant velocity, and still you'd have the same form of the equation. So generally speaking, if we said that the equilibrium equation, the equilibrium equation under the condition of elastostatic equilibrium, the elastostatic equilibrium, we can write this one as EQM, I mean equilibrium instead of equation, right? So this is the equilibrium equation. For the elastostatic equilibrium, it will be sigma Ji comma J plus the Fi, the same equation, but the right hand side definitely is gonna be zero. Why? There is no inertia, there is no acceleration, since we're already working as a static. So people agreed to give this equation a name that it is an equilibrium equation, which is typically the same like the equation of motion, but just for this special case that we have elastostatic equilibrium or elastostatic, so we used to give it a name as equilibrium equation. So if you try to even open any textbook on the continuum mechanics or linear elasticity, you're gonna find that all the time they give it a name as equilibrium equation. Equilibrium equation, because the concern of most of the continuum mechanics application that we are assuming that this object is already stationary, not moving. But there is a special situation that the object would be moving at a constant velocity and still having the right hand side term will be zero still. It means that while the object is already moving. So you should understand that the equilibrium equation, it is typically the same like the equation of motion, but for the special case that we have a static equilibrium of the continuum. And since we're already working with elastic objects, so this is the elastostatic equilibrium of the object. So this is the relation that relates, this is how the stress is related to the body force. And this equation, this is what we're gonna use all the time. This is the form of the equilibrium equation or the equation of motion that we're gonna use through the class. We have derived this one from these equations. This equation, this form of the equation, the dynamical form of the equation from the mechanics of discrete system of particle generally, but in the rest of this class, we're gonna consider this one as the equilibrium, and all the time this term will be zero. If we are interested, because here in this class we are interested in the elastostatic equilibrium of linear elastic material, we will not study any dynamical behavior of this elastic material. So that's why all the time this term will be considered zero in the rest of the class. Make sense? So this is this equation here. This is how the stress is related to the body force. So simply, if you already given a specific body force field, can we solve this equation for the stress field? Yes. If the F is given, you can find the stress. If the stress is given, you can find the force component. Very simple. Can we write this equation into the different components? So how many equations that we should end up with? Since this is a vector, also this term is a vector, we shall end up with 3 equations. And if you remember from the start of this class and our definition of the classical mechanics, we said that in the classical mechanics, the continuum is a composition of an infinite number of particles, and each particle is a point. A point, it has only one type of degree of freedom, that it can move along x, y, and z. It means that any point that belongs to the continuum or any particle that belongs to the continuum, it has 3 types of degrees of freedom. three degrees of freedom, which are displacement along x, displacement along y, displacement along z. So that's why the equilibrium equations or the equations of motion that have been derived are only three equations of motion. But if there are some more degrees of freedom to this particle, we shall end up with more equations of motion. But in the classical mechanics, and this is the main focus of this course, that we do have only three equations of equilibrium. If I ask you to write these equations along x and y and z, so simply, as you can see in this equation, within this term, j is a dummy index, but I, it is not a dummy index, because there is I here, but there is I here, but over two different terms, no problem. I'm talking about in the individual term, in the single term. In this term, j is a dummy index. It means that you can write this equation for the case that I equals x once, then for the case that I equals y another time, then I equals z another time. So we're going to end up with three equations. These equations relate the stress to the body forces. As we derived up before, three equations that relate the stress to the surface tractions, right? So simply here, the stress component, this x component, if in case that I is already x, so j is going to be general. I can write this equation as sigma j x comma j plus fx equals 0, right? But j is a dummy index. It means that it should be repeated. So once j is x and y and z, and you just gonna end. It means that this term, it will be divided into three terms at the summation of the three terms. So simply we can write this term as x comma x plus the sigma y x comma y. Now j is y. Now j is z. So x comma z plus the body force, which is just one term, as fx equals 0. And this is going to give us the first equation. The second equation, that now I is going to be y, still j is going to be 1x, 1y, 1z, three terms. So we're going to end up with three terms, as well as the xy comma x. This is j is x, but still I is y, plus j is going to be y comma y, plus the z, j is going to be z, y comma z, plus the body force along the y direction equals 0, and this is going to give us the second equation. Then how about the third equation? This is going to give us the sigma x z comma x plus the sigma y z comma y plus the sigma z z comma z plus the fz equals 0. This is the force component, the body force component along the z direction. So this is how the six stress components, sigma xx, sigma xy, sigma xz, sigma yy, sigma zz, and sigma yz, already related to the three components of the body forces, which are the fx, fy, and fz. As we discussed here, these are the relation of the body forces to the stresses through the equilibrium equation. Make sense? So let us consider an example on these equations, then we can move to another topic. So let us consider this example of the given following state of stress, sigma I equals sigma ji. It means that we do have a symmetrical stress tensor in a kinematical infinitesimal deformation with sigma 1, 1, sigma 1, 2, sigma 1, 3. We said that instead in some textbook they used 1 and 2 and 3 to refer like x, y, and z. So we could say that this is like sigma xx. This is the sigma xx is already given as a function of x, where x1 is just x. So this is going to be equal the negative of 2x squared. And sigma xy is already given by the negative 7 plus the 4xy plus xz, which is x3. And sigma xz is already given as 1 plus x negative 3y. And sigma yy is already given by the 3x squared negative 2y squared plus 5z. While sigma yz is already given by 0, and sigma zz is already given by negative 5 plus x plus 3, negative 5 plus x plus 3y plus 3z. So these are the different components of this stress tensor, the 9 components. One of these components is already 0, the others already as fields, as functions of x, y, and z. It is required to determine the body force components for which the stress field describe a state of static equilibrium. The condition is that we do have static equilibrium. It means that the right hand side of the equation, it should be 0. So how the stresses can be related to the body forces? The stresses can be related to the body forces through this equilibrium equation, that sigma gi comma j plus the body force, which is Fi, it should equal to 0, since we're already working in a static equilibrium. We can then write this equation into 3 different equations, right? But we should have the sigma ji, or the component of the stresses, which already given up there, but we have to do some derivative to this component with respect to x, y, and z. So it is advised to write the equations first to know exactly what type of derivatives that you need. So if we decided to write these 3 equations, the first equation is going to be sigma x comma x plus the sigma yx comma y plus the sigma zx comma z plus the fx equals 0. This is the first equation. And the second equation is sigma yx comma y plus the sigma yy comma y plus the sigma zy comma z plus fy equals 0. This is going to give us the second equation. The third equation is sigma zx comma z plus the sigma yz comma y plus the sigma zz comma z. Make sense? Plus fz equals 0, and this is going to give us the third equation. Make sense? So these are the, I'm sorry, this should be this term, this first term here, this term, this should be the sigma, because j is going to be x, y, comma x, then y, comma y, then z, y, comma z. Here we do have the, this also, it should be this term. It should be the sigma z, the sigma xz comma x, then y comma y, z comma z. This should be like xx, yy, z, xx, yy, z, and so on, right? And these are the different body forces. So we are interested in finding Fx, how much it is, Fy, Fz. So simply if we calculated these 3 terms and we move them to the right hand side, we're going to end up with Fx, the same for the other terms. So simply we can find this force component, but we need to find these derivative first, the sigma xx comma x, how much it is, and the other component. So simply if we decided to write the first equation, the sigma xx comma x, your objective is just to find the derivative of the sigma xx with respect to x, how much it is. Sigma xx, it is negative 2x squared. So its derivative with respect to x gives negative 4x. So the first term here will be negative 4x plus. How about sigma yx or xy? Because they should be equal according what he mentioned here, that sigma xx equal to the sigma, ij equal to the sigma gi. It means that it is symmetrical. So sigma xy should equal to the sigma yx, right? So in this equation, when it's sigma yx comma x, it means that the derivative of sigma yx, which it should be the sigma xy with respect to y. Sigma xy, we got it, or is already given here. The derivative of this term or this function with respect to y, the first term will be 0, the second term will be 4x, the third term will be 0. So the sigma xy or yx with respect to x gives 4x. Plus, how about the sigma xz or zx comma z with respect to z? Sigma xz is already given here. With respect to z, there is no z's in these 3 terms of the sigma xz. It means that this term, its z derivative will be 0 plus fx as you can equal 0. So as you can see, this term will be cancelled with this one. So we're gonna end up that fx definitely is gonna be 0. So this is the x component of the body force, it is 0 for this equation. How about the second equation, sigma xy, but with respect to y? We used sigma xy before, but we did derivative with respect to y. Now we're gonna do derivative with respect to x. Sigma xy with respect to x, which is this one with respect to x. The first term will be 0, the third term will be 0, the second term with respect to x is gonna give us yy, 4y. So this is gonna give us the 4y, this is the first term, plus the sigma yy comma y, sigma yy, which is this term. This is the sigma yy with respect to y. This is going to give us negative 4y because this term, these 2 terms will be 0. So this is going to give us here at the end the negative for y. Again, these two terms will be cancelled. The sigma zy comma z, zy or yz. Zy or yz both are zeros, right? The sigma yz is already given by 0. It means that the third term is going to be plus 0 plus the fy equals 0. It means that this term will be cancelled. This is going to end up with the sigma y is already 0 like the fx. Then how about the fz? Fxz comma x, fxz comma x. With respect to x, this is going to give us just 1 because this is 0, this is 0. With respect to x is going to give us 1. Here equals 1. The sigma yz with respect to y, sigma yz is already given by 0. So this term will be 0 plus 0. And the sigma zz comma z, sigma zz, which is this term, this sigma zz with respect to z, this is going to give us just 3, right? There is no derivative to all of these terms except the last term, which is 3z. It's going to be its z derivative will gonna give us 3 plus the fz equals 0. So we're gonna end up that simply fz is gonna be negative 4. So this is the third component of the force vector. So the body force vector is gonna be definitely 0 delta x plus 0 delta y, the y component, negative 4 delta z, which can be simply written as negative 4 delta z. This is the body force vector as required in terms of the stress component of this stress tensor. Make sense? So this is simply how we can relate the stress to the body force. So again, the stress can be related to the surface tractions through the relation. I forgot something. The name of this relation, by the way, it is known as the Cauchy formula. It is commonly known as the Cauchy formula. I forgot to tell you this thing. This relation here, the T, this one up there here. Yes, these relations, they commonly known as the Cauchy formula because this is the guy who already derived this formula. This is the Cauchy formula. And that's why, and this guy who first discussed these things of the continuum mechanics, he derived this, or he introduced this stress tensor. So that's why people give this name of the stress as the Cauchy tensor. This is the Cauchy stress tensor. This is the Cauchy stress tensor, right? So the stress is related to the surface tractions or the stress vector through the Cauchy formula. And this stress is commonly known as the Cauchy stress tensor, and this is what we're going to use in linear elasticity. This is the common thing in the classical mechanics of the linear elasticity. But the stresses are related to the body forces through the equilibrium equations or the equations of motion. Make sense? So these are two important topics that we should understand, and how the stress is related to the body force or the surface tractions. So that's it for this video. We have discussed two important topics. As I mentioned, how we can relate, or the stress, how it would be related to the surface tractions or the surface forces, also how the stresses are related to the body forces. In the next video, I'm gonna discuss the stress, how it would be related to the strain. We said that the stress and the strain, they already conjugate through something that we call as constitutive equations. So this is that we're gonna discuss. This is gonna be the focus of the next video of the next lecture. So next meeting, as I said, we're gonna discuss the constitutive equations, and we're gonna consider different forms of these constitutive equations depending on the different types of materials. Then we're gonna introduce the concept. Also, we're gonna discuss the concept of the linear elasticity or linear elastic material, which is the focus of this class. Make sense? So that's it, and thank you, and see you in the next video.